So our next speaker is Kai Selgrad, who's going to speak on a high-performance image processing DSL for heterogeneous architectures.
Okay, hi everyone. Can you hear me good? All right. So yeah, my talk is about our work on a high-performance image processing DSL. We call our DSL, wait a minute, Chipotle, but I will talk about that later on. First of all, when we talk about image processing, what we mean is mostly image filtering. So you have like an input image, like this is my Denmark vacation 2 years ago. And for example, if you want to find important edges in that image, you can apply smoothing and edge detection operations and end with an image like this one here, where you can really extract some information out of it. And there are a couple of different approaches to that problem regarding domain-specific abstractions. And I think a few of them use the same thing that we did, which is also inspired by previous work, where your abstraction is basically different kinds of operators you apply to the image. So the simplest one is like pointwise operators, where you have a pixel in the input image and you just map it to a pixel in the output image. So it's just a one-to-one mapping, which you can use, for example, for tone mapping or stuff like that. More complicated operators are local operators, where you have an area centered around that pixel and map the information stored in that area to a single output pixel. Okay, so that's the image processing part. The heterogeneous and high-performance part is that we want to have a language that we can compile to different hardware platforms. And so we're actually from computer graphics, so we do a lot of high-performance computing, where we use very expensive CPUs, where you also use very expensive GPUs. Some of us also look into mobile chips. And so you have very different hardware platforms, and they have very different characteristics. And even writing code that runs reasonable on a variety of such different platforms is challenging in itself. And even if you optimize it, on average, the result will usually be a bit away from being high performance. So there are some approaches for general purpose heterogeneous computation with high performance, for example, using the Open Compute language. But I think you still have to optimize a bit for the specific hardware you're targeting. There are also domain-specific methods. We list a couple of them in our paper. I will mostly restrict myself to HiPAC, which is something that I did at our which is something they did at our local university. Actually, one of our co-authors is also a co-author of the HiPAC stuff. So we also ensured that our comparisons are pretty fair. And also HiPAC is a tool that's really, really fast, and much faster than handwritten code usually. And when you use the HiPAC DSL, this is probably the worst slide you've seen in the entire symposium here. But I really wanted to put it all on one slide so you can get an impression of the amount of code and the style of code that they use. They embed their DSL in C++, and they do stuff like they have to write classes which derive from a specific kernel class, which encapsulates this image operator thing, and they look then for kernel functions that do convolutions, and here you see where they store the output to the single output pixel. And so this actually rather small piece of code generates very, very high-performing code for CUDA or for SSE or for AVX. And so being able to write that little code and get that higher performance is really a revelation for a C++ programmer to not have to do this all. Okay. But I think for the community here, it looks like lots of syntax, lots of boilerplate. I mean, what the hell is that thing doing, actually? And I don't expect you to understand it. But I think when I look at the literature for high-performance DSLs, most of the approaches usually rely on Clang or on LLVM or on both of them. They mostly strive for a C-like input syntax because in the high performance field, C is the dominant language. And of course, you get more users if you have a C-like syntax. Well, and also if you have your DSL code and you have Clang, then you can of course mix that freely with C++ code. And I think the reason they do it, first of all, LLVM produces pretty fast code, I think. And also Clang gives you a fully type-checked, fully analyzed tree, which of course helps you a lot. Okay, so HiPAC uses that tree for analysis, and for example, they hook at things like they try to find this kernel class, and then they substitute different code for it. So they analyze the tree, and then they substitute parts of it. And they go through great pains not to have to change the front end, because, I mean, who wants to change the Clang C++ parser front end? It's probably the gateway to hell, just because of C++. And so our claim is that the whole thing is pretty cool. I mean, you can take Clang and you can get a really detailed and analyzed syntax tree. However, we believe that it might just be a bit overly excessive to do that for image processing, because image processing, as you have seen, is pretty simple. And so we try to have a simpler solution. And our co-author, who did most of the work on HiPAC, he says what he spends most of the time while working on that is really picking out the appropriate details out of this humongous C++ syntax tree he gets. So that's probably the major productivity hindrance with that. And so what we want to do is we want to use a different approach that does not provide a C-like syntax, but it provides a Lisp-like syntax. And we compile the Lisp-like syntax to C, or to C-like language, mostly C++ and CUDA too. We presented that at ELS 2 years ago. And just to be clear, we do not cross-compile Common Lisp to C, because that's what the compiler guys are for. We just have a notation that looks, well, actually, there's a slide where you can see it. It looks pretty much like C with S expressions. And the nice thing is now that we have a C-like language in an S expression form, which allows us to do macros. And of course, when you do macros, we can do DSLs. And stuff gets really nice. But also, we've been working on this. I mean, we presented it 2 years ago. We put it on GitHub, I think, early last year. But it's still a side project. And so please try it out. It works. And I like it. But it's still like a little baby, yeah? So it's a bit beta-ish. Okay. And our code using C-Mera looks like this. I don't know how many of you are very proficient in C++. I mean, it's a highly advanced program where you see there's include statements and using namespaces. There's a function called main. It has a couple of arguments. We have this nice C++ 11 return type thingy. And the nice thing here is that you can, of course, use macros. For example, if you want to unroll the loop, you see here, we can just write a very little unrolling macro and substitute it here in the lower part. Oh, I'm shaking. And all it does, it loops over the sequence and it collects instances of the code. And of course, if we then generate our C++ output code, it looks like that. And I was pretty astonished when I went to my now co-author, to the HiPAC at our university, and I wanted to find out if this is something he might be interested in working with. And I showed him this example, and he was astonished. He was like, "Wow! If I have to do this in Clang, it will take me days." And I mean, this takes us 5 minutes, so that's got to be more productive. Maybe someone who's actually using Clang a lot can comment on that. Maybe later on. Okay, but to our image processing. To our image processing language. Do you remember the mess of code for the HiPAC I've shown earlier? It is compared to this little piece of code I show here. It's not the same filter we apply. It's a bit more complicated what we show here. But basically, the program consists of a filter graph. And the filter graph contains edges and nodes. And the nodes are the images that we work with. And the edges are transformations of the images. You can see the graph at the bottom of the slide. And so there's the same basic operations as with the HiPAC code, where there's there's a filter mask that was originally specified in the main function, and there's aggregators and operators showing how we combine the values of the filter mask with the image pixels and how we reduce all that together. In the end, we compute the absolute value, and then we store it to disk. So I think that's probably a lot more readable than the verbose C++ code. And you might notice that the graph shown at the bottom, that you can really see there, it's not really consistent. So we load something from disk, and then it's stored. We call it storage CPU because it's like in host memory. And then we want to compute a Laplacian kernel on that using CUDA, specified by the arch parameter up here. And so that doesn't really work like it is. So our system takes care to provide the images at the location where we need them, which is pretty simple, as we can just go over the entire code and find out which is supposed to go where and what are the dependencies of which step, so we can sort that. And we can, of course, compute the transition so that, for example, we copy stuff to the GPU here. And in the end, we copy stuff from the GPU back down. So we do some basic scheduling. However, we do not do more advanced scheduling. And this is something we want to have a look at in future work. For example, to find clusters of operations if you have a larger filter graph that you can just take and see, oh, there's few connections in, there's few connections out, so we just move that entirely to the GPU and do something in parallel on the CPU. That would be great, but we're not there yet. But I think that should be doable. Okay, one example that I want to show you that really shows why using a domain-specific approach can really give you performance you can't realistically achieve when writing the code by hand. Is an example here. You see the center pixel in black, around which we have an area of extent 3 by 3. You see it here. And towards the borders of the image, we have to take care not to access out of bounds naturally. And this is something that we do not have in our DSL. So the user code does not take care of that. So it is naturally provided by the language, which is simple. And we can naturally also do some simple stuff like pixels to the right of the center pixel. We do not have to check them against the left border and stuff like that. That's simple. But there's more you can do. So you can go and, depending on the extent of your filter, you can compute where you actually need to check stuff. So, for example, in the area labeled R here, you only have to check for the right border, whereas on the other side, you only have to check for the left border. I mean, that's pretty simple, but it results in the end, you don't have to check anything for most of the pixels. So usually you have filters like 7 by 7 or 17 by 17 or something, and you have images in the megapixel area. So you can really save a lot of computations here, especially when mapping to GPUs where conditionals are very expensive. And so, but to do that, you have to have you have to have different cases, and you have to replicate the code. And when you have something as simple as that here, we can just splice in the thing a couple of times. Whereas if you want to write that by hand and you have to maintain 10 different versions of the thing, it's just going to be painful. And so that's something. This is an optimization you can do with domain-specific approaches, but not really when writing code by hand. What was that? Okay. And the final example we show in our paper is we call it the night filter. It takes an image that is taken under daylight conditions, and this is really. Do you see anything on the lower one? Okay, it's a night filter. Stuff gets black. Awesome. Okay, maybe you can see that we preserve some edges around here, but okay, that didn't really work out. Okay, so you should actually see parts of the house, and you should see that stuff gets heavily blurred. And of course, you see there's reduced brightness, and there's also a shift towards blue. That's probably noticeable. And that's two filtering steps, or actually, there's a couple of blurring steps where we try to preserve edges, And there's one tone mapping step where you do the whole brightness reducing and blue shifting. And we asked Oliver, our HiPAC guy, to write this in HiPAC, and he ended up with 260 lines of code. And in our implementation, it's much less. And yeah, you could have probably guessed that from the examples I've shown. What is way more important for us is that also our DSL is much smaller. So we want to try different optimizations, and we're working on. I think one of the next things that's will be to do is having an AVX backend, and doing the whole scheduling stuff, and adding that to a very large system is of course a lot of work. And since we're all grad students working on that, we kind of want to have as little work for as much publication as we can get. I mean, it's true, isn't it? And so we're really happy that our system is a lot smaller than the competing system. And by a lot, I mean a lot. So it's like 50 times as small. To be honest, HiPAC does a couple of things more. I think they have 2 backends more than we do. So we do CUDA and SSE2. And I think they also do render script and some... there was another one, I'm not sure. But still, it's much smaller. In the 970 lines here, they do also contain our auto-vectorization for SSE2. They do contain a different code path for CUDA. So there's a lot in those, not even 1,000 lines of code. And to finally see, I mean, we try to do a high-performance image processing language, and in high performance, if you have nice abstractions but they don't perform, then of course you're kind of missing the point. So we checked, and our CUDA stuff is absolutely the same as using the state-of-the-art. Our SSE2 implementation is only half as fast as the state-of-the-art, but I'm pretty sure that's because Alex just did it in one afternoon. And also that's something, doing it in one afternoon is probably not enough to really know where to go in the HiPAC code, whereas using our thing, and knowing our thing obviously, proved to be really, really productive in that area. And so this is also when I told this to Oliver, who's working on HiPAC, and I told him, yeah, we did it yesterday evening, and yeah, he didn't believe us that we could do it that fast. Okay, so that's it from me. Wow, I must have spoken pretty fast. Huh?
Yeah, very fast.
Yeah, sorry.
So we have plenty of time for questions.
I tried to speak slower then.
Slide 15, please.
Slide 15?
Yes.
I numbered them. Oh, no.
Yeah.
Okay.
The questions, because you partitioned the domain into the ones with the special cases and the ones without.
Yeah.
And usually C++ compiler at least try to do this already themselves. So if you
Okay.
to de-loop, so they might end up with the same code. However, this is more robust, so the other one is fragile. But have you compared that actually?
We don't have taken the numbers, but it's an incredible difference.
Okay, so C++ compilers fail to do this themselves.
Yeah, they don't know the image dimension. So the image is just loaded, and you don't know. Then we actually, the produced kernel code, it's also funny. I mean, our implementation is 1,000 lines, and the code for the night filter that's generated is 8,000 lines of CUDA. Because the special cases get sequentialized, and we have one big CUDA kernel where it starts with a couple of go-to statements going to the right area, and then it just plows through that. And all the loops are unrolled, and that's so. I think the compilers do a lot, but I'm always astonished to see how little they do when you do stuff like that in comparison.
Because they're supposed to get that. At least if you count, if you hard-code the dimensions, they should.
Yeah, maybe if you hard-code the dimensions, but that's really cheating then.
I also see the point. It's better to have this way because that's what you want and not what you hope.
Yeah. I mean, we haven't tested it with a fixed-size image. Maybe we should do that, but I'm still pretty sure it's not as fast.
Yes.
So unclear, the code that you're writing is the DSL stuff.
Yeah.
Is that just the filters?
That's just the filters, yeah.
So it's not like a whole new program.
Oh, no, it's... Let me just get back to
Is
the...
that what the
That's the entire thing.
Okay,
So
that's actually, you could actually run that and say, because I don't know what image processing is, so you just put that in and you get an actual executable so that you can run that.
yes. So I think right now you're probably on the losing side if you specify 2 filter graphs, because then you will end up with 2 main functions. So maybe that's something we could change to just add a keyword that says, build me a main program too. Yeah.
Yes.
What are you doing in the borders when you have missing pieces? And the image you showed in red. Yeah, where did you get this from?
Okay, there's a couple of operations you can do. What we did is mostly inspired by OpenGL, where when you go out of bounds, you can either use a neutral element, or you can mirror back in so that you just go in that direction again, or you can repeat the image, where you then come in over here. So there's a couple of different things you can do, and which one is the appropriate one is it's application defined.
You can define it in DSL as well.
Yeah, you can specify it. Yeah. There's just a couple we did, yeah. Oh, and one thing I just remembered, I wanted to say that you probably see that in that example here we use this echo variable, for example, that is specified nowhere. And in our reviews, people were a bit skeptical about where they come from. And so, of course, there's lots of implicit names in that system. So I think here you see how we change the name of the accumulator to value, or the local ref and the relative coordinates. That's all stuff that's implicit. But you can specify the names for all those if you want to change them. And I think if we want to provide this to a larger audience, then we should sit down for an hour or two, provide some documentation where you can really understand what's going on.
Questions? Okay, thank you very much.